Welcome back, everyone. In this lecture, we're going to be talking about the z-test for one sample mean. In our previous lecture, we had talked about the major steps of hypothesis testing. And in this one, we're going to get a chance to apply those steps to our first inferential test, the z-test for one sample mean. So we're going to talk briefly about the z-scores for sample means and how they're z-scores, just like z-scores we've seen before. But the formula itself is tweaked just a little bit for computing for sample means. Then we're going to do a quick review of the steps of hypothesis testing, and then we're going to walk through a testing example using this z-test for one sample mean. The reading for this one is going to be Chapter 5, Module 9. Once again, this refers to the 4th edition of your course textbook. And before I jump into the next slides, I just want to let all of you know that I went back and listened to my first two voiceovers for the first two PowerPoints, and my goodness, I'm never going to be hired as a voiceover actor. So I'm trying to teach to a blank screen, and you're having to listen to this, so I apologize for my monotonous tone. I'll try to relax and bring a little bit more fun into it, but in order to make sure you're getting the information and make sure we're doing it as professional way as possible, I'm going to do my best to stick to the script. So once again, thank you for being you and working with us, and we'll get through this. All right, let's dive into z-test for one sample mean. Next slide. The first thing we need to realize is that when we're doing a z-test for one sample mean is that we need to look at how we're going to slightly tweak the z-score for a sample mean. So far, we have been using the z-score formula for individual values, and that was z equals your individual value minus a mean divided by a standard deviation. Well, now, in order for a hypothesis test, we're trying to figure out, as we talked about previously, is our sample mean common or rare? Not an individual person or an individual value, but the actual sample itself. Is that entire group, that sample, is that common or rare? So we need to make a slight tweak to our z-score formula. So as you'll see on this slide, I have written down, we will use a slightly different version of the z-score formula, etc. What you see here is we start with our raw score is not an individual value, rather it's x with the bar over it. X with the bar over it represents the sample mean. So we take the original sample mean, then we subtract the population mean, mu, and then we divide by something called the standard error of the mean. And the standard error of the mean is kind of like the standard deviation of the sampling distribution of the mean. But for right now, just pay attention to what it's composed of. So when we look at that standard error of the mean, you'll notice it is sigma divided by the square root of n. So what are those basic pieces? Well, sigma is the standard deviation of the population, and then n is your sample size for your sample. So in order to get a z-score for a sample mean, we need to have 4 pieces of information. We need to know the sample mean that we have, the sample size we are working with, and then we also need to know 2 pieces of information about the population. What was the population mean that we're comparing our sample against, and then what was the standard deviation from that population? Next slide. So quickly to review our hypothesis testing steps, you'll notice we still have our 6, then the 7th with confidence intervals, which will come in our next lecture, added at the bottom. We're still going to start with, we need a research question. We then need to translate our research question into 2 competing statistical hypotheses, the null hypothesis and the research hypothesis, HO and H1. We then are going to set our level of significance, our degree of rarity, which is alpha. And as always, we will set that at 0.05. We then need to determine the critical value of our test statistic, which is based upon the level of alpha and the particular test that we're doing. We're going to be doing a z-test, so we'll see how that works. Then we move on to step 5. In step 5, we need to compute our observed value of our test statistic. So since we're going to be doing a z-test for one sample mean, we need to compute our value of z observed. In step 6, we will make our decision. Do we reject the null hypothesis and go home with H1? Or do we fail to reject the null hypothesis and end up with HO, right? We have to choose one or the other. And then in our next lecture, we'll talk about what we can do with confidence intervals if we can reject a null hypothesis. Next slide. So our example, in this case, we have a Z-test for one sample mean. In order to conduct a Z-test for one sample mean, we have to think, what are we doing? Well, what happens in a Z-test for one sample mean? That's when you compare known population information against some sample. And when you're thinking about why would I do that, well, you want to know, maybe it was known in the population that the average rate for a certain crime was a certain value. And you want to know, has it changed over time? Or if you want to compare known population information from one state or jurisdiction versus a small sample from another state or another jurisdiction and say, is there a significant difference between my sample and that known population information? You could do a Z-test for one sample mean. So let's break it down looking at this. We start with known information about a population. So let's say, in our example, that population data from 1990 showed that the average weight of male inmates in prisons was 200 pounds with a standard deviation of 40. Okay. And let's say that in recently collected sample data, we found that a sample of size 100 inmates of male inmates showed the following, that the sample size was 100 and the sample mean average weight was 210 pounds. This is going to lead us into a comparison to say, is our sample with a mean of 210 pounds different from the known population of 200? Or in other words, we may think, have people changed? Has the average weight of male inmates changed since 1990? So let's move on to the next slide. Next slide. All right, so the first thing we start off here with any hypothesis test is the statement of the research question. So our Z-test will compare the sample data with the population data in order to see if the sample mean appears at what we've used all the way along is common or rare. If the sample is deemed rare, we can conclude that the average weight of male inmates has changed. All right, so when we think about that, we're saying, like, why do we want to do that? Well, we want to know whether or not our sample data is rare enough that we say, oh, something has changed. This doesn't appear to be a common sample that would have originated from that same population. So we look at the note. Note, we will be conducting a two-tailed test. So as you may have recalled at the end of our last lecture, I talked about we will always be doing a two-tailed test. So we're not going to try to predict an increase in weight, a decrease in weight. No, we are simply going to try to examine change. Is there a change? Is there a difference? And you'll notice those are non-directional terms. I'm not saying increase. I'm not saying decrease. I'm simply saying change or difference. So when we set up our research question, we want to make sure it reflects that. So we look at our research question, it says, has the average weight of male inmates changed since 1990? All right, next slide. Step 2 of our hypothesis test. Now we need to take that original question, has the average weight of male inmates changed, and translate it into two competing statistical hypotheses. So on this slide, what we're looking at is we're looking at how we translate the words, the verbiage, into actual testable hypotheses. And so you'll notice on here I have HO and I have H1. HO is the null hypothesis. So you may recall null always means no. So if the question was, has the average weight changed? The null hypothesis says, no, it hasn't changed. Well, if it hasn't changed, then it should still be 200 pounds. Because recall, the population data from 1990 said the average weight was 200 pounds. So if it has not changed, it should still be 200 pounds. So that's why we write the null hypothesis as HO, where mu, because we're trying to predict mu, equals 200. And this reflects no change from the old population. On the flip side of that coin, we have the research hypothesis. The research hypothesis says, yeah, there has been a change. The average weight of male inmates has significantly changed. Well, in order to represent that as our statistical hypotheses, we have H1. And H1, once again, you'll notice we have it as mu because we're trying to predict the population. We have it as mu does not equal 200. And this would reflect any change from that original value of 200. So two final things to look at. When you look at the way that we have written HO and H1 on this slide, you'll notice that HO, the null hypothesis, says there's been no change, and that's reflected by saying population mean equals 200. H1 says population mean does not equal 200. So when you look at these two things, you notice two things. One, they are what we had referred to before as mutually exclusive. So HO and H1 are mutually exclusive, meaning you can't be in both categories at once. You're either equal to 200 or you're not equal to 200. Second thing we talked about with statistical hypotheses is that they have to be exhaustive. And once again, HO and H1 are exhaustive, meaning they cover all possible outcomes. So whatever the new population mean happens to be, it's either equal to 200 or it's not equal to 200. So not equal to 200 means it could be less, it means it could be more, but it covers all possible outcomes. All right, let's move on to the next step. Next slide. All right, so step 3, we are setting the level of significance. This was alpha, the degree of rarity required to reject the null hypothesis, as we saw in the previous presentation. We also, as we saw in the previous presentation, we're going to set alpha at 0.05. That is the industry standard, the acceptable value. So from here on out, for any hypothesis test we do this semester, just assume alpha equals 0.05. Alpha equals 0.05. That's where we're going to start, and we'll leave it at that. Next slide. Step 4. Now we need to determine the critical value. Since we are working with a z-test for one sample mean, we are working with the z-distribution. So if we're working for the z-distribution, our critical value, and you may recall from before, the critical value is the value of the statistic that draws a line between common and rare outcomes. Since we're working with the z-distribution, our critical value will be a z critical value. Also, since we are doing a two-sided or two-tailed or non-directional test, we are going to be having our rare area split into two ends of the distribution. We set alpha at 0.05. So we said in order to get a rare value of a z-statistic, it has to be out to the point where 5% or less of the total area under the curve is where it would fall. Well, but we have to split that 5% in half. So when we split it in half, we get 2.5% at the low end, 2.5% at the high end. And when we look at that on a z-distribution, we notice that the z value that corresponds to having 2.5 below a certain number and 2.5% above a certain number, that z-score becomes 1.96. And if you're unsure about how this came about, look back to that area under the standard normal curve handout that I provided in class. That's also available on Beachboard. And you'll notice if you look up a z-value of 1.96 and look at the C column, you'll see, sure enough, that the area that lies beyond it is 2.5%. So that's what we see illustrated here. So when we take an alpha of 0.05 and then know that we're working with a z-distribution, that translates into a critical value of plus or minus 1.96 for this test. Let's move on to the next slide. Next slide. Step 5. So in step 5 now we've set our alpha, 0.05. We have determined the critical value, determined by which distribution we're working with, which happens to be the Z distribution. So our critical value became 1.96 because we split the rare areas into both corners or both tails of the distribution. So 2.5% of rare area in both, which led to a Z value of 1.96. So we set that. Now we need to look back to our actual sample data and figure out, well, okay, so we had a sample that said the average weight of inmates was 210 pounds. So let's break it back down. We want to know, well, we know 210 pounds in our sample is greater than the old 1990 population data that said 200 pounds was the average. We know that. But is it far enough away from that old population to say that our sample is rare? And if it is rare, it means things have changed. So let's reiterate that. Our sample appears in raw units to be greater than the old population. Our sample mean is 210. The old population that we're comparing it against is 200. But that 10-pound difference, is that enough to say that our sample is so rare that it most likely came from a population that was not centered around 200? That's what we're trying to figure out right now. So we need to take our sample data and compute our observed test statistic. So when looking at that, we're going to use the Z-score formula that we saw from a few slides before, and we're going to compute the observed Z-score. So you'll notice Z, what we're trying to get, equals our sample mean of 210 minus the old population mean of 200 divided by the standard error of the mean. And the standard error of the mean is composed of the population standard deviation of 40 divided by the square root of the sample size, which was 100. So you'll see how the formula breaks down here. We end up with a 210 minus 200 divided by 40 over the square root of 100 equals 10 over 4 equals an observed Z-score of 2.5. So that we need to write down. And remember, for our particular sample, we got an observed Z-score of 2.5. Now, that value is going to tell us just how common or rare our sample happens to be. Let's move on to the next step. Next slide. All right, now that we've established our hypotheses, alpha, critical and observed value of our test statistics, we need to make our decision. So for this first introduction to inferential statistics, our first test, our Z test for one sample mean, we are going to do it by comparing our Z observed that we just computed on the previous slide to the Z critical value that we figured out in step 4. So our Z observed was 2.50. Our Z critical was 1.96, positive, negative 1.96. So to keep it short, and then I'll explain a little bit more on the next slide, because our Z observed is more extreme, meaning further out into the tails of the distribution than Z critical, we are going to reject the null hypothesis. So we're happy. At the end of this test, we actually got what we wanted. We rejected null, and we concluded that, yes, we have found a difference. Yes, we have found a change. We have found a significant outcome. Okay, but we'll step back in a moment and figure out how that is. So the one thing to look at here is look at our Z observed, 2.50. And when I say it's more extreme, meaning the absolute value 2.5 is greater than the absolute value 1.96. That's it. That's what I mean by more extreme. So let's take a look at that on the next slide. So next slide. All right, so here is where I explain what I mean by more extreme in more detail. the absolute value of Z observed was higher than the absolute value of Z critical. Therefore, thinking back to drawing out a distribution, Z observed, 2.5, falls in the rare area of the distribution, those shaded blue areas that we saw from a few slides ago. Our sample was rare enough to conclude that the average weight of male inmates is not equal to 200. And in fact, the average weight has changed. That's what we get a chance to conclude here. And then you'll notice below the double lines on this slide, I say if the opposite had happened, what would we have concluded? So if the absolute value of Z observed had happened to be lower than the absolute value of Z critical, we would have failed to reject the null hypothesis. What does that mean? Well, failing to reject the null hypothesis means there is not enough evidence to conclude that HO is not possible. So it sounds sort of backwards language, but in this step 6, remember we have two choices. We either reject the null hypothesis and conclude that the research hypothesis is true. That's what we did. We rejected the null hypothesis and concluded that the research hypothesis was true. We had a observed score of 2.5, which was greater or more extreme than the critical value of 1.96. So we rejected the fact that the population mean was 200 and says, nope, it has in fact changed. If we had not come to that decision, we would have done what is known as failing to reject the null hypothesis, and that's the lower part of this slide once again. And failing to reject, you never accept the null hypothesis, you just don't reject it. And if you were in class when I gave the example about, yeah, you may recall or may not recall, I'm not going to go down that. I'm not going to go down there right now. But you don't want the null hypothesis, but you got to go home with something. Maybe that'll jog your memory. So you got to go home with something, and if you got to go home with a null hypothesis, that's failing to reject. So let's take one more closer look at that on the next slide. Next slide. All right, so in our example, we rejected the null hypothesis and concluded that the average weight of male inmates has changed. So our next logical question is, well, if the average weight is not 200, then what is it? Right? We made the decision that we rejected HO equals 200. So we rejected that. And we said, we concluded HO does not equal 200. So we're saying it's not 200. So the logical question is, well, what is it? And to answer that question, we're going to turn to confidence intervals in the next presentation. Take care.